Hello everyone, welcome to Cell and Gene Therapy Manufacturing and Commercialization Digital Week. We have a great lineup of presentations over the next 2 days, providing you with exclusive insights into cell and gene therapy analytics, process development, manufacturing and supply chain strategies. My name is Nicole Lumley and I'll be your host for today's session titled Model-Driven Synthetic Biology Approaches to Engineer Improved Stable Cell Lines for Lentivirus Manufacturing. First, I'll cover a few housekeeping items. If you do experience difficulty with audio or advancing slides, refresh your screen with F5. If you're experiencing other issues, hit the question mark button to receive assistance. At any time during the presentation, submit your questions into the Q&A window on the left-hand side of your screen. In 24 hours, you'll receive a link to watch the recording of this session. Let's now begin by introducing our speaker, Brianna Jayanthi, Senior Synthetic Biologist at Asimov. Thank you for joining us today. Now I'll hand over to our speaker to begin the presentation.
Hello, and thank you for joining me today for this webcast as part of BPI Cell and Gene Therapy Manufacturing and Commercialization Digital Week. I'm Brianna Jayanthi, a synthetic biologist here at Asimov, and it's really my pleasure to share with you today about LV-Edge stable systems for lentivirus production. So at a glance, the LV-Edge systems are stable packaging and producer cell lines with the viral components integrated into a HEC293T chassis. Both systems achieve high performance, achieving up to 1E9 TU per mil for therapeutic transgenes, and allowing for a reduced cost of goods, de-risking the supply chain with reduced needs to procure critical materials. So the outline of this talk, I'll give you a bit of an overview of Asimov. I'll share details of our LV-Edge packaging system. And perhaps I'm most excited to share our just released LV-Edge producer cell line overview. And finally, I'll wrap up with a summary of Asimov's capabilities and how we can help you across your manufacturing needs. Asimov is a tools company that integrates biology and software. We start with GMP-baked host cells, CHO, HEC293 and 293T, and a library of well-characterized genetic parts. We develop data-driven models to guide our designs along with scalable processes. And finally, we wrap all of this in our computer-aided design software, kernel, for powerful advancements to manufacturing. Our platforms can be accessed through two distinct business models: tech-out licensing, where we transfer our tools into your lab and support you through deployment, or through internal services, such as the case with our stable producer cell line development. We currently have 30+ partnerships across the industry. We have tools that support manufacturing along 4 main pillars. We have established solutions for CHO-based biologics production and are developing pillars for RNA and gene therapies. Today, I'm going to focus on our capabilities for lentiviral manufacturing for ex vivo cell therapies. Transient transfection-based lentivirus production is a standard across the industry and benefits from rapid development timelines, which really facilitates speed to clinic. But sourcing of 4 GMP plasmids along with transfection methods lead to risky supply chain and complex non-scalable manufacturing. Our off-the-shelf semi-stable packaging cell line option de-risks the supply chain and lowers the cost of goods by reducing the need to a single transgene GMP vector that is transiently transfected into our cell line with a well-defined process. And finally, our fully stable producer cell line further de-risks that manufacturing and provides scalability on demand to meet larger patient populations. As I'll show later, our fully stable producer offering also enhances productivity or titer per volume. And together, our semi-stable packaging cell line with the transfection of your GLI plasmid and our fully stable producer cell line offerings complete the LV-Edge system. Now I'll get into some details and performance of our packaging system. The three cornerstones of our LV-Edge packaging system are our packaging cell line, our unique DNA design capabilities, and our robust platform process. Our packaging cell line has the provenance required for GMP manufacturing. We source the cell line from the European collection of authenticated cell cultures. We engineer this by our expert team in Boston, Massachusetts, USA, under rigorous regulatory standards. We clone out and suspension adapt into a chemically defined media. And we currently have a research use cell line available with our GMP bank release in just a couple of months, mid-2024. Our packaging cell line has been engineered with all the lentiviral components needed to make VSV-G pseudotyped lentiviral vectors. VSV-G, GAGPOL, and REV, all under tight inducible control. And transfection of your GLI, along with addition of an inducer molecule, allows you to produce titer virus. Now to our DNA design. Our CAD tools improve titers. At the left, I'm showing you Kernel, which is our Asimov-developed, intuitive-to-use computer-aided design software that has a construct designer linked to our library of well-characterized genetic parts, a sequence viewer, and our unique sequence optimizer. To the right, I'm showing you the performance of our sequence optimizer. So early on in development of our LV-Edge system, we noticed that better transgene expression led to improved titers. And this led us to further explore sequence optimization across three clinically relevant CAR payloads. In the top in the black is the original innovator sequence, and bottom in pink is our Asimov optimized sequence. Across these three transgenes, we see a 4 to 17-fold improvement in functional titers. The gray bars in the middle are third-party comparison sequence optimizers. And you see varying levels of improvement dependent on the transgene for these third-party optimizers, whereas Asimov sequence optimizer leads to consistent improvement across transgenes. Now I'll talk about the development of our platform process. Using model-guided process development, we developed a robust, scalable, and ready-to-transfer process for our LV-Edge packaging system. To do this, we took a three-phase approach. Our phase one was thorough characterization of growth phase. Phase two is similarly thorough characterization of production phase. And phase three is process optimization that spans both growth and production. We performed over 250 bioreactor runs. 8 parameters were calculated and tested at 3 scales. This led us to a well-documented, ready-to-transfer with ease process, and it's supported by our experts. On the left, I'm showing you one example. On the right, I'm showing you one example of how our process was informed by computational models. A functional titer as a function of 2 process variables, A and B. Functional titer shaded in pink, darker is better. And X indicates our training data that we fed into our model, and O's indicate the design candidates. Importantly here, the design candidates that lead to best optimization were outside the regime of our training data, signaling that we may have missed this particular optimization without the benefit of our model-guided development. So to sum up, our packaging cell line has the provenance required for GMP manufacturing. Our computer-aided design of DNA improves titers through sequence optimization. Our process models allowed us to define a robust, high-performing process. And when you use our LV-Edge system, you get all of these supported by our expert technical team. Getting into the performance of our lenti packaging system, we looked at 3 distinct CAR transgenes. We cloned the gene of interest into our transfer plasmid backbone. We transfect that GOI into our packaging cell line and measure titers by an adherent HEC293T-based transduction flow cytometry method. And across the 3 transgenes that we looked at, we see close to or exceeding 1E8 TU per mil for unconcentrated harvest. Anti-BCMA is approaching that 1E8, and Yescarta and Kymriah CAR gene sequences lead to lentivirus with E8 or right above E8 TU per mil titers. So I just showed, and I'll continue to show throughout this presentation, titer data. So I want to describe for you a little bit our flow titration method. During development of the LVH system, we sought a biological assay that would show us impact of genetic system and process changes. We also wanted to give consideration to the use of unconcentrated virus, and this flow cytometry method allowed us to iterate rapidly. So we seed our HEC293T adherent cells and add varying amounts of crude lentivirus containing supernatant. At the high amount of virus addition, we confirm the presence of virus, and the other 2 addition, lower volume addition of virus, we look for a sweet spot of % positive events that provides accurate calculation of the true titer. And importantly, we've confirmed our methods and the values that we get out by outsourcing qPCR-based titration. And we leveraged the wide-ranging expertise within the Asimov team and developed a flow cytometry analysis Gaussian mixture model that accurately describes our positive transduced and negative cell populations. This makes our cytometry analysis more robust. And to the right, I'm showing histograms with this Gaussian mixture model populations identified. In pink is positive and purple is the negative cell population. The 293 T cells transduced on the top with vectors containing an original CAR sequence, and the bottom lentivirus vectors containing the same CAR that has been sequence optimized here at Asimov. We see a 1.3 time % increase in transduced cells, and which indicates an increase in titer, and a 6x mean expression increase indicating an increase in potency. So we wanted to confirm the quality of the virus we were generating in our packaging cell line with the ability to transduce primary T cells, also accounting for donor variability. So we obtained apheresis from 3 donors, isolated CD4 positive and CD8 positive T cells, cryopreserved those. This allowed us to then thaw and activate, followed by transduction and expansion of the transduced population. In the center, I'm showing flow cytometry plots on the top, non-transduced cells, and the bottom, transduced cells. And to the left, again to the right, I'm showing you how we use % transduced cells to calculate a functional titer. Again, Asimov sequence optimization provides us a 15-fold improvement in titer. We do observe donor variability as expected. Absolute titers are also lower than what we calculate with transduction in our HEC293 T cells, not unexpected. And here we are titering with viral samples that have been through freeze-thaw cycle, and we see an impact on that, on the viral particles due to that freeze-thaw. But overall, the packaging system generates quality lentivirus material across 3 CAR transgenes, Yescarta, anti-BCMA, and Kymriah sequences. Rounding out the attributes of our packaging system is genetic and expression stability up to 60 generations without any antibiotic selection pressure. Expression is stable regardless of passaging schedule, 3 passages per week versus 2 passages per week on the top. And on the bottom, we see stable DNA copy number for all 3 integrated vectors, VSV-G, GAG, and REV were measured here. So So that concludes the data I'll share today for our off-the-shelf semi-stable LVH packaging system. And I'm excited to next tell you about our just released fully stable LVH producer system. When you access our LVH producer cell lines, you'll get a high titer RCB just 4 months from transfection. During these 4 months, we move seamlessly through single adherent transfection and selection steps, suspension adaptation of stable bulk pools, single cell printing and clone screening, scale up and RCB generation, AMBER 15 clone verification, and RCB release. We perform this work in our state-of-the-art facility located in Boston, Massachusetts, and are outfitted with industry-leading equipment to move through single-cell cloning, that bioreactor, and up to benchtop scale verification. And we ensure quality through a myriad of analytic capabilities. We start generation of our fully stable producer cell line with a single co-transfection of 4 plasmids designed for stable transposase-mediated integration and tight inducible expression. We generate our bulk pools in triplicate to ensure robust performance. Once we have a stable adherent bulk pool, we then remap those cells off of serum and suspension adapt into a chemically defined media. The right chart shows functional titer of 3 CAR transgenes. Again, our favorites, Kymriah, anti-BCMA, and Yescarta. Sequences. Our adherent bulk pools consistently titer around 1E7 TU per mil. Following suspension adaptation into that chemically defined medium, we see around a 2.5 to 3.5 fold increase, leading our suspension adapted bulk pools to achieve mid-E7 TU per mil. Briefly describing our cloning process, we start by seeding clones using a single cell printer. We perform industry standard monoclonality verification that meets regulatory needs using the cell metric instrument. And we use a proprietary clone screening method to select our top clones, then scale those up and measure clonal titers by our flow cytometry transfection assay. When we clone out of our suspension bulk pool, we achieve greater than 7-fold increase from pool to top clone consistently across our 3 CAR transgenes. Our proprietary clone screening method allows us to scale a limited number of clones and measure titer by transfection assays, and our top clones reach mid-E8 TU per mil titers in shake class. We again wanted to verify the quality of the lentivirus we were generating with this fully stable producer system with the ability to transduce those primary T cells. We follow a very similar process to what we used previously. And in the center, I'm showing those flow scatter plots for non-transduced and transduced isolated T cells. And at right, I'm showing you how we use our percent transduced cells to calculate a functional titer. We see excellent correlation between the titers calculated in HEC293 T cells and the primary T cells, while the absolute titers are lower for T cells than that calculated from HEC293T, not unexpected. And we do observe the expected donor variability. Overall, the LVH producer system generates quality lentivirus material across donors and transgenes at high titer. Again, leveraging our model-guided process development capabilities, we're able to achieve 1E9 TU per mil titers for our producer cell lines. Starting from the bioreactor process developed with our packaging cell lines, we use a similar model-guided approach to further improve our producer process, leading to up to 5-fold increase when we scale from shake flask into an AMBER 15 microbioreactor environment. Across clones and transgenes, we maintain or improve titers, and again, we're able to achieve 1E9 TU per mil, or close to for two distinct CAR transgenes. And finally, we do see good expression stability across a number of our fully stable clones. We cultured for 70 generations without any antibiotic selection pressure, 5 clones for 2 independent molecules, or a total of 10 clones. And we see less than 5% variation from the start of culture duration. And now I'd just like to wrap up. Taking the Kymriah CAR transgene as a case study, Asimov offers capabilities to achieve more than 1E8 TU per mil titers across manufacturing systems. Our sequence optimization alone can improve titers up to 5-fold in a fully transient system. Moving to the semi-stable LVH packaging system, which de-risks manufacturing, we maintain those E8 TU per mil titers. And then moving into our fully stable LVH producer system, further de-risking manufacturing, improving scalability, and productivity. We achieve up to 1E9 TU per mil. And so I'll just end with reminding you that our LVH system is really a flexible, comprehensive kit of modules to aid your lentivirus manufacturing. We offer a semi-stable packaging cell line option that reduces cost of goods. Our sequence optimization increases titers and potency. We have an internal team of molecular biology experts that perform DNA synthesis and cloning, providing ready-to-test optimized plasmids. And we have a platform process for our cell lines that produces with reliable protocols and off-the-shelf material. Our producer cell line provides scalability on demand that allows you to transition and meet larger patient populations with scalable, high productivity, and all of the optimization supported by our experts. And I'd like you to keep an eye out for some additional capabilities with an expanded genetic parts library and vector design simulator, as well as independent model-guided process development. And thank you so much for joining me today to learn how Asimov's LVH stable system can support your lentivirus manufacturing across every phase of development. And I'll be pleased to take any questions.
Lovely. Thank you for an excellent presentation. We've received a few questions already, but we'll give the rest of you a moment to enter your questions in the Q&A box to the left of the slides. Before we begin the Q&A, I'll run through some brief announcements. First, I'd like to thank our session sponsors, Asimov, BD Biosciences, and Rentschler Biopharma for your support. And next, I'd like to quickly draw your attention to our face-to-face Bioprocess international events and digital weeks, a full schedule of which you can see at bioprocessevents.com. Now we'll begin with the Q&A. So the first question is, can you go straight from a packaging to a producer cell line?
We can. We prefer to go from a naked host, if you will, to the producer cell line with a fluid plasmid transfection, because then we're not locked into a ratio between the VSV-G, GANPO, and Rev elements.
Brilliant. And next question, does your host cell line contain the large T antigen?
Yes, the chassis for our packaging and producer cell lines is a HEC293T cell line, but we are working and making rapid progress on a 293T based offering.
Brilliant. And next question, can you tell us any more about the clone screening method?
Unfortunately, I cannot. I really wish I could, because this was an exciting process to develop, one that we iterated on a few times to land on something that works really well across gene sequences.
Lovely. And is clumpiness a concern for your suspension HEK cell line?
Yeah, I think it's pretty typical to see clumpiness for suspension hex cell culture. We do have some clumpiness as we're starting from a non-clonal host, but we also have internal methods to incorporate clumpiness as a screening metric for our clones.
Perfect. And the final question that we have is, have you looked at PI ratio of the virus?
We have. We're still in the process of confirming those values before we want to share in such a public forum, but we're excited about what we're seeing there and hope to have that data in the coming weeks.
Lovely. Well, thank you for such a great session. If anyone submitted a question that wasn't addressed, keep in mind that the speaker will reach out to you directly. This session was recorded and you'll receive a notification in 24 hours when the on-demand session is available for viewing. Before you log off, please take a moment to complete the feedback form so we continue to improve our Digital Week experience. On behalf of Informa Connect Life Sciences, have a lovely day.